Yeah, so today we'll cover quadratic function, and then after that I will go back to piecewise defined function. That should take us approximately 1 hour, a bit more, at most 2 hours, but should be less. And then I go on to 2.7, which will not be in our test 1. So your test up to 2.6 only. Okay, but the one we learned today is actually the very easy part that I don't mind to put into the test tomorrow. Okay. In other words, if you don't get what you learn in this 2.5, 2.6 today, basically you don't study my lecture today. Okay, the domain for polynomial, like including quadratic function, is all real numbers. Now, how about the range? The range depends on how we know the graph actually dancing. We start from y squared, which is from 0 to infinity. The range is 0 to infinity, and they move 3 units to the left. The range stays the same because I just move it to the left. Okay, and then we shrink by a factor of 1/2. So what will happen is -3, 0. Instead of going up 1, we go to 1/2 only. Instead of going up 4, we go up 2 only. So you will see the graph is chubbier because you shrink that. You shrink that vertically by a factor of 1/2, and then we move 4 units down. Now, moving 4 units down is the one will change the range to -4 to infinity. Okay, so later on the graph will approximately look like that. The range will be -4 to infinity. Now, how about the axis of symmetry? The axis of symmetry is x equals to -3. The vertex originally 0, 0, because we move 3 to the left and 4 units down, the vertex is now -3, -4. The y-intercept, we plug in x equals to 0. That's 9/2 minus 4, that's 1/2. So the y-intercept will be 0, 1/2, while the x-intercepts, we set the y equals to 0 and solve for x. So 4 equals to 1/2 x plus 3 multiplied by 2, and then apply the square root property. So I get plus minus square root of 8 equals to x plus 3, and continue on the right hand side. So x plus 3 equals to plus minus 2 square root of 2. So x is -3 plus minus 2 square root of 2. I need to write them in coordinate form. That's -3 plus 2 square root of 2, 0, and -3 minus 2 square root of 2, 0. Okay, now if you want to plot these coordinates later on the graphing paper, the one that I have on the to the right of that, then you may need to use calculator to compute the approximate value of these two numbers here. So the one I shade in yellow, we call that the exact form. Now, but if you want to plot that, you may prefer to know what they are in decimal. Okay? Now, like using these informations, then I plot the coordinates. The vertex is -3, -4 is here. The axis of symmetry is here. This is the axis of symmetry. X equals to -3. Okay. Now, if you don't have graphing paper, then you cannot just use this dot. You need to write that -3, -4. Okay, if you don't have graphing paper. That's why I suggest you to have a graphing paper. Okay. Now the thing is then, oh yeah, the y-intercept is 0,1/2 is here. It's 0,1/2. The x-intercept, I need to use calculator. The x-intercept, I need to use calculator, but I can do it later. Okay, I can do it later. How do I get the other 4 coordinates beside the vertex? Yeah, you need to give me these 4 coordinates. Now we know that for quadratic, once we have the vertex here, we move 1 unit to the right, 1 unit up. Supposed to be going up 1, but because we shrink it by the factor of 1/2, we go up only 1/2. Likewise, when we go to the left, 1 unit, supposed to go up 1, but we shrink that by 1/2, becomes going up only 1/2. When I go 2 units to the right, I supposed to go up 4, but because I shrink that by factor of 2, by a factor of 1/2, I go up only half of that 4, which is 2. Likewise, when I go to the left, this far. When I go 3 units to the right, I'm supposed to go 9. 3 to the right, I'm supposed to go up 9. But because of that shrink by 2 becomes 4.5. And you see, I actually get that this coordinate here. So when I go 3 units to the right, I go 4.5. 1, 2, 3, 4.5. You see that? Okay. Now, because it is symmetric with respect to the axis of symmetry, then when I go to the left, I will get the same thing. Now, if you want to make it even, quote unquote, finer, you get more coordinates. If you want to get more coordinates, you can do the following. When I go 4 units to the right from the vertex, supposed to go up by 4 squared, which is 16. But because of shrink by 2, it becomes going up by 8. So when I go 4 units to the right, 1, 2, 3, 4, I go up 8. 4 plus another 4 here. Now, with more coordinates like that, then the graph will be smoother. Okay, the graph will be more smooth. Now, the one that I need you to give me, of course, always the vertex and the other 4 coordinates here. The one I shade in yellow is the one required. Okay, the one I shade in yellow is the one I required. And sometimes if it is clear and easy, I would like you to give me whatever you can plot on the coordinate system. Okay, but if you ask me what's the minimum, Thomas, then the yellow one. How about the blue one? To be honest with you, usually I don't penalize unless I see that it's way too easy that I'm supposed to penalize. Then I will penalize half point maybe. Okay, but basically put as many coordinates that you can put in there. Okay, the one that is considered important coordinates. Now let me put it here. Let me graph them smoothly. I try to graph them smoothly, honestly, and that's why I get more coordinates. Okay, now then from here we see one thing, that the x-intercepts are, let me put this color here. The x-intercepts are, this guy is, oops, too big. Use another color. Yeah, this guy here is between -1 and 0. This is between -1 and 0. While the one here, the other x-intercepts here, this x-intercept here, is between -6 and -5. -6 and -5. Okay, so if you later on actually use your calculator, this will be -0 point something, 0, And this guy here will be negative 5 point something, comma 0. Now, then you can try using your calculator to confirm. Okay, you can use your calculator to confirm. Now, from here, I actually want to say more things. The reason I show you the graph first here, because I want to show you two very, very important phenomena, two very, very important property that we get from this quadratic function and the graph. Notice that if we had the x-intercepts, then the axis of symmetry will be the midpoint of those two. To be more precise, the midline. Okay, so we can say, note that the axis of symmetry is given by x equals to a number, right? Now, can be done, maybe I write it in more appropriate way. Note that the axis of symmetry is, well, because it is axis of symmetry, is the midpoint, the midline to be more precise, of the x-intercepts. So, if we know the x-intercepts, if we get x-intercepts, then let's say the x-intercepts are R1 and R2. R1, 0, R2, 0. Then the axis of symmetry is given by x equals to R1 plus R2 over 2, the midpoint. If you happen to have the x-intercepts, okay, and they happen to be, let's say they happen to be a nice number, then you can do the midpoint. Now here, actually, in this example, your R1 is negative 3 plus 2 radical 2. Your R2 is negative 3 minus 2 radical 2. When I add them, I get negative 6 and these two cancel. Right? Now then when I divide by 2, I get negative 3. Notice that that's what we have for our axis of symmetry earlier. Right? Okay, so you can also find the axis of symmetry by first finding the x-intercepts. Okay, by first finding the x-intercept. Okay, let's go on further. Furthermore, I think it's supposed to be one word. Furthermore, we know that the roots, of a quadratic equation ax squared plus bx plus c equals to 0 are given by R12 equals to negative b plus minus square root of the discriminant over 2a. So looking back, R1 equals to negative b plus radical d over 2a. R2 equals to negative b minus square root of d over 2a. When I add them, R1 plus R2, they already have LCD. I get negative db plus radical d plus negative b minus radical d over 2a. That gives me, if you distribute, and you will see negative, the radical d, that radical of the discriminant cancel negative radical d. So we will get negative 2d over 2a, which is negative d over a. That's the sum. The sum of two roots of a quadratic equation is negative b over a. So the axis of symmetry now can be done by dividing that negative b over a by 2. That's the axis of symmetry. Okay, now notice that this is if we have the standard form, the general form, the general form instead of the standard form. Like from this standard form, you can see directly where's the vertex, negative 3, negative 4. Okay, and therefore you will know the axis of symmetry is x equals to negative 3. However, we anticipate later on that the function given to us in general form. Now, if you have general form, then you can find the x-intercept first, and then the midpoint will be if you the midline, which is the axis of symmetry, or if they happen to be not factorable, then you can just use this formula, negative b over 2a. Okay, that's for the axis of symmetry. Maybe I summarize that here. Therefore, the axis of symmetry of fx equals to ax squared plus bx plus c is given by x equals to negative b over 2a. So this is the alternative way to find the axis of symmetry from a general formula, the general form of a quadratic function. Again, you can find the x-intercepts first and then divide by 2. You can also do completing the square first, and then so you complete the square and then you get this form here. Okay, then you can read the axis of symmetry. So getting the axis of symmetry is actually something quite common. Now, suppose we have axis of symmetry. How do we find the vertex? The vertex is always, the x component of the vertex is always the axis of symmetry. So what we have here will be the x component of the vertex. Now then, the y component of that, basically you plug that value into the vertex. Okay? Yeah, let's do one problem. Suppose, for example, I have let fx equals to x squared minus, what is good? 4x minus 12. That's way too big. Maybe +3. Change that to +3. Let me change that to +3 first. Now then, from here, the domain is all real numbers. That one is for sure. The range, I cannot ask you that yet. I think the y-intercept is standard. The y-intercept will be 0,3. That's easy. Part C, how about the x-intercepts? Set the y equals to 0, and if you can factor, you have to factor, otherwise I give you 1 point penalty. Keep that in mind. I get x equals to 3, x equals to 1. So the x-intercepts are 3, 0, 1, 0. Now then part D, how about the axis of symmetry? Now you can do it this way. The first method, you say x equals to the midpoint of the x-intercepts. So that's 4/2, that's 2. Remember, it has to be the equation of a vertical line. The second method, which will give you the same value, is you use x equals to -b/2a. Okay, so the a equals to 1, the b is -4, the c is 3. Right? Okay, which if I go on further, that will give me negative of -4 is 4/2, that's 2. So yes, we expect to get the same axis of symmetry. Now then, how do we find the y component of the vertex? For the vertex, the x component will be the same with the axis of symmetry, but then how to get this guy here? The vertex must be on the graph. The vertex must be on the graph of the function. So what I can do is I plug in that tool into the function. Okay. I plug in that tool into the function. Whatever the outcome, 2 squared minus 4 times 2 plus 3, there will be 4 minus 8 plus 3, that's -1. Now that -1, the outcome of that function at 2 will be what you get here. That's the y component of the y component of the vertex. I prefer actually this method, by the way. I prefer this method to find the vertex. If we start from standard, if we start from general form, then we won't be able to read the vertex right away, right? If we start from standard form, the one that we have above, you can read the vertex right away, right? From here, you can read the axis of symmetry and vertex right away if you start from standard form. However, if you start from general form like this, no, you have to do something to get the vertex. Okay, now the first method is using axis of symmetry, and then from there you get the vertex. There's another way, actually, another way. The y component of vertex in a quadratic equation, quadratic function, is given by -d/4a. -d/4a. I will use this method. I recommend you to use. You can use this method. You can use this method if you have computed at the discriminant available. already. Now, it's usually you compute the x-intercept, and if it's not factorable, then you will use quadratic formula, right? Okay, now when you compute your quadratic formula, then you must have computed your d, the discriminant, then you can use it here. Okay, now suppose I apply this here anyway, even though I already know that the y component of vertex is -1, but suppose I use this formula. Now the discriminant is -b minus 4ac. 16 minus 12, that's equals to 4. So the y component of the vertex is -d over 4a. -4 over 4, that's -1. Notice that that's what I get here. That's the same number I get. Okay. So, well, if you do so, you basically need to memorize more. Okay. If you do so, you basically need to memorize more. Anyway, once I get the vertex, strangely, let me just go here. Then what is this fx in standard form? Fx in standard form. So you know the function is a quadratic function. The leading coefficient is 1, right? The leading coefficient is 1. And then the vertex is 2, 1. So what will the standard form be? The standard form will be 1 for the leading coefficient, x minus 2 squared plus, minus 1. It should be minus 1 here. Okay, so fx equals to x minus 2 squared minus 1. That's the standard form. Now, the way I do this problem, basically have this interplay. I will do one final example from here. So when you have quadratic function, either you are given standard form, which is fx equals to a of x minus h squared plus k, or you are given general form. Fx equals to ax squared minus bx plus bx plus c, where the a here is the same to the a there, but other than that, they are different. From standard form, we can read easily the axis of symmetry, that's x equals to h, and the vertex can be read easily h comma k. Okay, while from general form, the one we can read easily, actually only y-intercept, 0, c. But then, because we're supposed to get used to deal with quadratic equation, general form, so you are expected to be able to find the x-intercept here, okay, either by factoring or completing the square, or formula, quadratic formula, to get the x-intercepts. Now then, the axis of symmetry, you can get either by getting the midpoint of those two x-intercepts if they happen to be nice numbers, or you can use x equals to negative b over 2a. While the vertex will be the x component will be the same through the axis of symmetry, while the y component, you can use formula negative d over 4a, but if you don't memorize that, you can just plug that into the function. Negative d over 2a, when you plug that into the function, the output will be negative d over 4a. You can try to do the algebra there. Okay, now then, the thing is then, once you get axis of symmetry, or to be more precise, the vertex, that's basically what you have here. And therefore, you will be able to go back to find the standard form. Okay, so that's the big plan. Okay, so from general form, we get the x-intercept, y-intercept, axis of symmetry, vertex, and therefore we get the standard form. Now, what if we have standard form? How do we get the axis of symmetry? How to get the vertex? It's also there. We can read it there. The y-intercept, how to find the y-intercept if you have standard form. Then compute it as usual, set the x equals to 0. So you will get 0 comma something. Okay, how about the x-intercept? You set the y equals to 0, but I believe eventually, so you will get something comma 0, something comma 0. Now you may use square root property there. The way I did this, this is the way I did it. That's the square root property method. You isolate the perfect square and then apply square root both sides. Don't forget the plus minus. Now then, once you get x-intercept, y-intercept, of course you can get, in both cases, once you get the vertex, you can find the range. Depends on if opens up or open down. You may have a question, Thomas, so how do I come from standard form? How do I write it in general form? Now, if you have that kind of question, very likely you are thinking too hard. What the heck, Thomas, what you're saying? I ask you a question and then you say I'm thinking too hard. How do I convert this into general form? Just FOIL it and combine like terms. Ta-da! Now you know why I say you're thinking hard. So this is fx equals to 1/2 times x squared plus 6x plus 9 minus 4, which is 1/2 x squared plus 3x plus 4.5 minus 4. Actually 9 over 2. Let me use 9 over 2 instead. Which is 4 over 5. And this is equals to 1/2 x squared plus 3x plus 1/2. Okay, that's the general form. So to convert from standard form, from this standard form to general form, just FOIL it. Okay, now how about from general form to standard form? Well, you can do completing the square, but if I were you, I will find the vertex first. It's a lot easier. I will find the vertex first. Then from the vertex, I can find the standard form. Okay? Now, so what happened is this though. I hope you're aware that, yes, I know that you can read your book. But if you, do you know how many people are attending the class right now? Only 2, including me, 3 people. And that has been the case so far. I have when I see how many people actually watch my lecture video, of 7 students, only 4 regularly watch, 1 on and off, and the other 3 is it's never, if it's never, then it's rare. But it's your problem. I said since the beginning of the class that it does take some maturity level for you to be successful in this class. Now, let's do problems. Let's do problems. Let's say I pick questions from page 160, so from our exercise, from exercise number, let's say we have number 12. So fx equals to 2 over 5x squared minus 12 over 5 plus 23 over 5. The main question is find the standard form. Express in standard form. Or write in standard form. Ax minus h squared plus k. One way I do completing the square. The second way I find the vertex first. Okay. Since this is a pre-calculus class, I show you both. First method, completing the square. So I will factor that 2/5 out. So x squared, this is with x here, minus 6x plus 23 over 2. Actually, I don't need to factor that one out there. Let me not factor that one out. So let me just factor this part here. Plus 23 over 5. So I just factored from here. I just factored the 2/5 from here. Okay. Now then I will complete the square here. I will multiply, I will add by 9 and then subtract by 9 at the same time to cancel that at 9. How do I get 9, Thomas? Why not 10? Why not other number? Because of this. If you remember how we complete the square, -6 divided by 2. The leading coefficient has to be 1, remember? That's why I factor that 2/5 out. Okay, now once the leading coefficient is 1, and then the middle numbers, divide by 2, I get -3, and then square it. That's how I get that 9. Now, then, the first 3 terms here will be a perfect square. While this guy, later on, I distribute that with that 2/5. Okay, so I will get 2 over 5 x squared minus 6x plus 9 minus 2 over 5 times 9 plus 23 over 5. This is equal to 2 over 5 x minus 3 squared minus 18 over 5 plus 23 over 5, that's plus 1. Okay, that's the standard form. Now, I personally prefer to do it by finding the vertex. Okay, so the second method is The second method is find the axis of symmetry first. Find axis of symmetry. That will give us the x component, and then the vertex that will give us the x and the y component of the vertex, and therefore we can find the standard form. Okay, so the axis of symmetry, that will be x equals to negative b. What is b? Negative of negative 12 over 5 over 2a. Which is 12 over 5 over 4 over 5. Multiply the top and the bottom by 5. I get 12 over 4. That's equals to 3. So the axis of symmetry, x equals to 3. Therefore, my vertex must have 3 comma something. Okay, now how to get this thing? You can plug that 3 into the function. So f3 equals to 2 over 5, 3 squared, okay, minus 12, is it 12 over 5? Yeah, minus 12 over 5 times 3 plus 23 over 5. This is 2 over 5 times 9 minus 12 over 5 plus 3 plus 23 over 5. That's 18 over 5 minus 36 over 5 plus 23 over 5. That's 5 over 5, which is 1. Cool. Then once I get the vertex, then I can go into standard form. Fx equals to the leading equation 2 over 5, x minus x component of the vertex squared plus the y component of the vertex. You see, we get the same thing. Okay, so what happened in completing the square method? Okay, we try to do these 2 steps in the method 2 in one single step. So it's kind of like heavier. Okay, it's kind of heavier. Now, why I prefer the second method? Because somewhere in between, we usually need to answer axis of symmetry and vertex anyway when I ask you quadratic function. Right? When I ask you quadratic function, I usually ask you the axis of symmetry and vertex anyway. Okay, now that's number 12. Let's say number 22, or maybe number 22. Yeah, that's right. Number 22. Fx equals to 2x squared minus 4x minus 11. The question is find the zeros, maximum or minimum value, and then graph. Find the zeros, basically find the x-intercept. The zeros, find the zeros. Let me define it first. Definition. The zero or zeros of a function fx are all x such that, maybe I don't use x, all c such that fc equals to 0. So when I say, for for example, if I say 3 is a 0 of fx, if you see that sentence, it means f3 equals to 0. Okay, that's what it means. So if they ask you find the zeros of this function, then you basically solve it, set it equals to 0, and solve for x. I will use quadratic formula. So a equals to 2, b equals to -4, c equals to -11. So the discriminant will be b squared minus 4ac that's 104. So the roots are -b plus minus square root of 104 over 2a. That's 4 plus minus 2 square root of 26, because 104 is 4 times 26 over 4. Okay, so x1 is 4 plus 2 radical 26 over 4. I can factor by 2, cancel with 2 of the bottom, give me 2 plus radical 26 over 2. And x2, you will see that will be the conjugate of that. Yeah, if you do it long ways, you will eventually see that this, if the discriminant not a square number, then the solutions will be two conjugate, two numbers that are conjugated to each other. Now, that's the zeros. Okay, so follow-up question, call that A star, then what is the x-intercept? Find x-intercepts. The zeros of the function, just numbers. X-intercepts, however, is a coordinate. Okay, now then part B. Part B, find the maximum or minimum value. Well, before we answer that question, let's figure this out, that if the A is positive, then it has minimum, no maximum, because the parabola opens up. If the leading coefficient is negative, then it has maximum, no minimum, because the parabola opens down. Now, in this case, because the A is 2 over 5, which is positive, then has minimum value. Now, what is the minimum value? Y minimum will be the Y component of the vertex, -d over 4a. We computed the d earlier. The discriminant is 104, -104 over 4a. So Y minimum is -104 over 8, that is -13. Let's go on with the follow-up, V star. So what is the vertex? We know the minimum value is -13 using the formula. But how about the x component? Well, remember I said that we can use the roots or the zeros of the functions, right? And then you add them divided by 2. But you will see this is the same to negative b over 2a. Okay, so if I use that negative b over 2a, I will get 4 over 4, which is 1. That will be my vertex. Now then part C. Then part C, what will the graph be? I know the vertex already. So let me write it in standard form. So fx now equals to, it's supposed to be 2x squared minus 4x minus 11. The leading coefficient is 2. The vertex is 1 comma negative 13. So x minus 1 squared minus 13. That's what the standard form. Then how do we graph that? How do we graph that? Let me grab my graphing paper. I think my graphing paper is not. Let me give you a break first, and then later on, in between, I will show you the graph. Okay, right now is 12:07. I give you a break for 10 minutes. We come back at 12:17. Okay, let me continue. I was replying another student's email who dropped the class. And want to rejoin the class. Okay, let me put this back.
Professor, I had
Yes.
a different question. So, like yesterday, the ICA decided to I was.
Yeah, we saw earlier that the function is fx equals to 2 of x minus 1 squared minus 13, which means the vertex is 1 comma negative 13. Let me put it here. Okay, this is the vertex. Okay, now then, how do we sketch the graph from here? Now, you see this factor 2. It means we stretch that vertically, by 2. Okay, now what does it mean in the graph? Means when I go 1 unit to the right, I'm supposed to go up 1. Now I multiply up by 2 instead. When I go to the right 2 units, I'm supposed to go up 4. But because I stretch by 2, I end up going up by 8. When I go 3 units to the right, I'm supposed to go up 9. But because multiply by 2, I end up go up 18. 9, 12, 15, 18. And using symmetry, I do likewise here. So the curve now is stretched vertically by a factor of 2. I'm sorry, my daughter is like crying so loud. So this is the parabola. It's not a nice one because I cannot graph it on paper. Okay, let me go on with one more example or two more examples. I think one is good. One is good. Let's say number 26. Oops. Number 26. I will not graph it. They give us the graph, but I will not graph it. Number 26. The question is to find the standard equation. Find the standard equation of the quadratic function They say parabola, I prefer to say quadratic function whose graph is given. Is given, and the graph is something looks like this. It looks like this. Oh. It looks like this. You can see from your book, but the important one is that they give us the vertex is -1, -2, and there's another one coordinate on this graph 2, 3. Now then, how do I use these two informations to find the equation of the function? Now keep in mind that this one guy here is the vertex. This guy here is the vertex, and that's a very big information. Why? Because once I know the vertex is -1, -2, then I know the function must be a times x plus 1 squared minus 2. Right away, from the vertex, I get this and this. Okay, now the only other informations we need is how to find the a, and we get it from replacing the x and the y by 2 and 3 respectively. So basically f2 equals to 3. At the same time, f2 means 2 plus a times 2 plus 1 squared minus 2. So 3 equals to a times 9 minus 2. So 5 equals to 9a, a equals to 5 over 9. So the quadratic function is fx equals to 5 over 9 x plus 1 squared minus 2. Okay, now suggested homework from here. I don't want you to do too much from here though, because I need you to focus on your test tomorrow. I would like you to do from this section 2.6, suggested homework. Of course, if it is during regular time, I will tell you to do all as much as possible. But this is basically the minimum I would expect you to do. I would like you to do number 7, and then number 11, and then number 19, and number 21. Maybe with number 23 also. That's for now. Yeah. Okay, but when you do these problems, whatever functions you get, answer these questions. You need to find the domain is always all real numbers. That one, pretty much nothing to worry. Okay, but and then y-intercept, x-intercept, axis of symmetry, and then vertex, and then standard form. Standard form. There are some of them I believe you can try to sketch the graph. I think you can try to sketch the graph for number, let's see. I think you can try to sketch the graph for number 19. And then number, yeah, try to sketch the graph for number 19. But you will see this kind of question in my old test also. I always have this kind of question in my old test, one. Okay, right now it's 1:03. Let me give us a break. We come back at 1:13 because we talk too much. Piecewise define function. piecewise defined function is basically a function that is defined piece by piece. A function defined piece by piece. So let me go ahead with an example. Suppose, for example, we have a function fx equals to, let's say, 2x minus 1 for x greater equals to 1. And then absolute of x plus 2 for x less than 1. So when we say piece by piece means in this domain, this is the function we graph. In this domain, this is the function we graph. That's actually what it means. Okay, so it seems to be complicated, but the idea is actually quite simple. Now let's put them in practice. Give me a second, use my graphing. Okay, in practice, let's see, suppose this is my graphing paper. Okay, and then I want to graph this, right? Let me move this. Yeah, I'll leave it here. Okay, so I will first graph this. Okay, 2x minus 1 is a line with y-intercept 0, -1. The slope is 2. So the line supposed to be, that line supposed to be the connection of all these coordinates here. That's what the line supposed to be. Okay, that's what the line is supposed to be. Okay, now the thing is, it is only for x greater equals to 1. So anything not in x greater equals to 1, I will erase. So the graph we are dealing with is, for the top one, is that. Okay, now then, so let me use yellow marking here to show you what's the graph. Okay, but you don't need to shape this actually though. I just try to show you how they are related. Now then, for x less than 1, we use absolute x plus 2. Now absolute x plus 2 is phi whose vertex is at -2, 0. Okay, and it's actually like this. So the graph of this absolute of x plus 2 looks like this. And here, I suppose to go indefinitely far, but the thing is when I look at the rule O for x less than 1, so up to, I'm sorry, I think I make it wrong for the first one. Supposed to be x less than greater equals to 1, so it's actually here. While the guy here only up to x equals to 1, not including, so I use open circle. Okay, so this is for the first part, the first piece, and this is the second piece. Again, you don't need to highlight that, but I need you to do this. This is the one you need. Close circle, right? And then the line. Okay, and then this is the phi, the absolute value. All of them included, so the line until here, it's open circle. Okay, now that's the piecewise defined function. Let me erase the shading. here, solid circle here, and then erase the shading here. Like this. Okay, so if you put the coordinates, that would be best. Sometimes we don't have eraser, right? Or we can't make it smooth, but at least you put the coordinate right on the grid. It does tell me what it is. So this one should be open circle. This one should be open circle. Okay, basically, therefore, using this function, f3, because 3 is greater or equals to 1, then I will use 2 times 3 minus 1. How about f0? Now 0 is less than 1. It goes to the blue piece. Then this will be absolute of 0 plus 2. That will be 2. Now what happened right at 1? What happened right at 1? Now x equals to 1 is in the yellow one, the yellow piece. Right? So I need to use the yellow part. That's 2 times 1 minus 1. That's equals to 1. Now from here, then I also introduce you to some notation. In calculus later on, we know this as a limit notation. Okay? Now, I need you to learn this notation now. As x approaching 1 from the right-hand side. This is x approaches 1 from right-hand side. So if I approach the x equals to 1, this is x equals to 1 here. When I approach 1 from the right-hand side, now the graph will be approaching the value, then x is approaching the value 1, okay? Fx approaching 1. As x approaching 1 from the right-hand side, what happened to the y value? What happened to the function? Now, notice that if I use other notation, as x approaching 1 from the left-hand side, if I approach x equals to 1 from the left-hand side, then the value is approaching, then fx will be approaching will be approaching 3. Okay, this is from left-hand side. Now, from this figure also, we can say the following. What happened as x approaching infinity? Basically, if you go very, very far to the right, so if you extend this graph here indefinitely far, right? Okay, indefinitely far, then what happened to the value of the fx? Then fx will go to, as you can see, the larger your x, the larger also your fx, right? In fact, it goes to infinity. As x goes to negative infinity, what happens? If you go very far to the left instead, if you go very far to the left instead, what happened to the value of the function? If you go very far to the left, if you continue on, you will see that the function actually gets to then fx going to infinity. Now we know this as a limit notation. We know this as a limit notation. To play more about this limit notation, let me take a look on number 56. Number 56, I try to sketch the graph. It won't be super precise with number 56, but I hope it's close enough. Number 56, we have, let me use that 2, 3, so it's open, it's closed circle here, and it's open circle here. It goes like this. And then this is -2, -3, and it looks like this. And then here we have this guy. So the coordinate here is -2, 4. The coordinate here is -2, -3. This is 2, 3. This is 2, 1. This is 5, 0. And this goes to down there, and this goes horizontal to the left. That's what the graph looks like. Now then, let's see. Part A, as x approaching 2 from the left-hand side, what happened to fx? So where's my 2? When x approaching 2 from the left-hand side, so from here, this is x equals to 2, right? This is x equals to 2, but you approach from the left. Now on the graph, then you will be traveling this way. Then it approaches what? It will approach 3. So it will approach 3. What happens if we approach 2, x approaches 2 from the right-hand side instead? So this is the 2, x equals to 2. You approach it from the right-hand side. This is the 2. I approach it from the right-hand side. The closer I am to x equals to 2, what happened to the y? And we see the y gets closer to 1. Now part C, as x approaching -1. Now they don't tell us, do we approach the left-hand side or approach the right-hand side? Okay, -1 is here. This is -1 here. Now notice that the value at -1 is this. Either you approach it from the right-hand side or you approach it from the left-hand side. You will still get the same value of y either way, and that is -2. Okay, now to be more precise, we will say the following. Let me say this. Because this is actually something formally done in your papers later on. When we say as x approaching -1, then we need to see what is x as x approaching -1 from the right-hand side. What happened to the value? Approaching what? It's approaching -2. What happened if we approach -1 from the left-hand side? Also approach -2. Only if the left-hand approach and right-hand approach give us the same value, then we can say without left right here, then it's approaching the same number. Okay, now what happens if they don't approach the same number? What happens if they don't approach the same number? Let's say from part A and part B. From the left-hand side of 2, the value of the function approach 3. From the right-hand side of 2, the function approaches 1. So what if I ask as x approaching 2 without specifying from left or right? Now, because the left-hand limit and the right-hand limit are not the same, the left-hand limit is 1, the right-hand limit is 3, then fx approaching the limit of fx, we say, does not exist. If the left-hand limit and the right-hand limit are not the same, then the limit approaching 2, if we don't specify the left-hand side or right-hand side, we say does not exist. Okay, now let's go on further. Part D. What happens as x approaches infinity? When you go very far to the right, what happened to the value of the function? Apparently, you can see this guy here is actually going down, right? Okay, so we will say it goes to negative infinity. If you super extend that to the right, what happens if x going to very far on the left-hand side? If x going to negative infinity, what happened to fx? And you see that this is horizontal line here when it goes to the left. Okay, so as it goes to the left, it will approach 4. Okay, it will get closer to 4. Now in chapter 4, we will learn, actually chapter 3, the end of chapter 3, we learn rational functions. And that's where we see what we call far ends behavior. Far end behavior. So this guy here, as x approaching infinity, that's actually the right hand behavior, far right end behavior. And this guy here is far left end behavior. So if you go very far to the right, what happened to the value? If you go very far to the left, what happened to the value of the function? Okay, yeah, but for now, from the graph, we expect you to be able to read the limit condition here. Okay, so from this section, what do we learn? Besides what we learned yesterday, we learned piecewise defined function. And then if I give you a piecewise defined function, can you read the limits, especially at the points where discontinuity happens? It gets discontinuous, right? Like in this case here, in this picture here, we get discontinuity at 2. We get discontinuity at 2. Why? When we approach negative, not 2, I'm sorry, negative 2. When you approach negative 2 from left-hand side, the value gets closer to 4, right? But when you approach from the right-hand side, the value gets closer to negative 3. Okay? And what we meant by discontinuity is basically that when you approach from left-hand side, it's not the same to if you approach from the right-hand side. Then it is discontinuous. Okay, yeah, there's actually other reasons for discontinuity though, but once the left-hand limit and right-hand limit are not the same, then it triggers discontinuity. Okay, yeah, it triggers discontinuity. There's another type of discontinuity. Let me do one more problem, but this time I make it a bit harder. Okay, this time I make it a bit, not harder, let's say it's more complicated. For example, suppose I have let fx equals to, let's fx equals to, let's say square root of x for square root of x minus 2 for x greater than 3. And then, how about absolute of x maybe plus 1 for x between -2 and 3. And then negative x minus 3 for x less than equals to -2. We'll try to sketch the graph and, if possible, deal with the limit problems. But we need to sketch the graph first. Let me move it here. Let me move it here. Easier to see. Okay. And 3 or greater. Let me color this yellow to grab our attention. This is for greater than 3. 3 or greater. I will use square root of x minus 2. That's the square root of x moved 2 units to the right. 2 units to the right. So the graph actually looks like this. Supposed to look like this. Supposed to look like this. Supposed to look like this. Okay. Now, however, it's from 3, greater than 3 though. Okay, greater than 3. So I need to erase this. Let me erase this first, but I need to erase this too. And in fact, the endpoint's not included. So I need to use open circle here. Okay, this is our square root of x minus 2. Okay. Let me do this. This is my square root of x minus 2 for x greater than 3. Okay, now let's deal with the second one. I will use blue color. Absolute of x plus 1. Absolute of x plus 1 is the graph of absolute of x that I move 1 unit up. So I move 1 unit up, then it looks like this now. The vertex is 0, 1, right, up to 3. So this one here is closed circle. And this guy here down to -2, x equals to -2, but not including negative. Now the last one, so let me change that to blue color. This is absolute of x plus 1 for -2 less than x less than 3. How about the last one? Negative x minus 3. The y-intercept 0, 3, but the slope is -1. So the slope is -1. That's a line that looks like this. That's a line that looks like this. Supposed to be this line. However, it applies only for x less than equals to 2. Okay, so I need to erase this. Okay, that's the graph. Let me change the color so that you can see which color corresponds to which part. Okay, negative x minus 3 for x less than equals to -2. Now, then I need you to answer this question. As x approaching -2 from the left-hand side, what happened to fx? What happened to the value? So when I approach -2, this is -2 here. When I approach -2 from the left-hand side, then my y gets closer to -1, right? How about if I approach from the right-hand side, as x approaching -2 from the right-hand side? Then fx will be approaching -2 from the right-hand side. Then the value will get closer to -3. Okay, now how about as x goes to infinity, for example? As x goes to infinity, then fx approaching what? This guy, the red one, when you go to infinity, if you go very, very far to the right, of course, it will keep on increasing, right? So as x goes to infinity, fx goes to infinity also. And what happens if we go very far to the left instead? Then fx equals goes to also positive infinity here. If you go very far to the left, then you will go very far up for the y. Okay. Now from this 2.5, continue from yesterday's suggested homework. 2.5 suggested homework part B. But I have to be honest with you. This section here is more about your understanding about notation. Okay, number 49, number 51, number 55. I think those 3 questions are good enough. So up to here, we get the material for your test 1 tomorrow. That's the material for your test 1 tomorrow. And I really hope the material that we learned today is actually just a little bit more from what we learned yesterday. Okay, so tomorrow you have your test for the whole period. Okay, from 11 o'clock to 2 o'clock. You need to stop writing at 1:45 so that you have enough time to upload your informations on campus at 2 o'clock. Okay, can I use cheat sheet, Thomas? Yes. Can I use open book? Yes. The only thing I don't want you to do.
We can use a cheat sheet?
Yeah, I say cheat sheet, huh?
Oh, we can also see the book?
Yes, I don't mind you to do that. The one I don't want you to do is I don't want you to cheat from other students or somebody else. You're on your own.
Oh, okay. But we cannot see from our notebooks, right?
It's okay too. I don't mind.
Oh.
As long as it's not from somebody else.
Oh, okay. So I can like look up any like notes I took like the past week and then like do my.
Yes, I don't mind. But here's the thing though. Here's the thing. If you rely too much on your notes or your textbook or your cheat sheet, for example, I prefer you to do cheat sheet. If I were in your place, I will do cheat sheet instead. Okay, and not looking at the book. But here's the thing. The reason is because you may actually think that you can study during the test, but you run out of time because you spend more time studying instead of working on the test. That's actually a trap there.
Oh, yeah.
You see, right? So what happened is if you try to look for the solution, look for the similar questions from the past, there's a chance that you forget about the time and the time just keep on thinking and then you forget to turn it in.
Yeah.
I don't want that to happen, and that's why I will not extend the time.
Okay, got it.
Okay, so here's what happened. Here's what happened. In the past, I know that some students cheating, and I let it happen. But when they cheated, they forget about the time. They cannot turn it in.
Oh.
Okay, and then I told them, no, I'm not taking it. They insist I need to take it. They send it to me by email. When I look at their tests, you can tell right away these students actually cheating from each other. So I tell them to drop the class. You know,
Got it.
be careful. I try to give you guys less pressure, right? But at the same time, because of that less pressure,
What
you
if we
may get slack off with
accidentally
slack off into forgetting about the time.
got
Yes.
it. What if we accidentally do the incorrect solution with someone that I don't know?
What do you mean?
Like we get the exact same wrong answer, but we didn't cheat from another.
I learned statistics. I can tell.
Okay.
And actually, you don't need somebody with statistics. I can show you the difference between two people making the same mistake, unintentionally, of course, and two people making exactly the same mistake.
Got it.
Repeatedly.
Okay.
Okay. Put it this way. This is not recorded, right? Let me stop recording. Put it this way.